It's been a while since we met. Hopefully everyone had a good vacation or time off, or hopefully you did something. I know a few of you stayed at the hostel there. So, and the week before, I had a physical therapy on the Monday, so therefore I can't. So it's been a couple of weeks since we've met there. So, and as promised, I'm going to go ahead and kind of wrap up the robotics part of the class. I mean, we didn't go into much depth. That was kind of the intention, was to not go into much depth. So I'm going to kind of go through these slides relatively quickly. Then I'm going to go through a set of slides where I talk about introduction to industrial automation and PLCs right there. So, okay, with that said, and right there. Okay, so these are the slides I used last time, and again, they're just kind of introduction to industrial robots. We did talk a little bit about Android robots and some things like that. I will have a review before I put that there. Actually, since it's an online test, I don't really need a review because you can look up answers and consult among your friends. Do the wiki thing there. So, okay, right there. So this particular set of slides is really, I think, where I ended up last time. And I pointed out that a couple of these slides would be on the final exam and definitely on the midterm. But their introduction robotic automation, advantages, disadvantages, types of automation, and this there. So this kind of goes back to the very beginning of the semester. There. So, and because we haven't talked for a couple weeks, and this is really kind of the review of everything on the robotics, it's just well to go back to the beginning and just kind of hit topics. So a robot is a machine that can be programmed to perform a variety of tasks. Very simple. It's a very broad term, simple to complex devices. Anything from Panasonic is coming up with a machine that works with a washer and dryer setup that when your clothes are done, the clothes come out and the machine, I shouldn't call it a washer dryer because now it also will fold your clothes and put it on shelves. So, I mean, I would consider that type of home automation or robot right there. I have at my house for my wife's use although I'll use it for time, something called an iRobot that goes through and vacuums the floor. There's also a model out now that will mop your floors right there. So there's machines that will cut your grass if you happen to live in an area where you use a lawnmower to cut your grass. The 3 laws of robotics, these have been around for a long time. A robot may not injure a human being through inaction or allow a human being to come to harm. That's an interesting one. And I have a new pen and it still doesn't work right. Still, if I draw a line here, it shows up on the top. I draw a line under the word harm. That's there. So it's the projector. But a robot may not injure a human being or that there. That's an interesting law and one that is not being followed today. There's a lot of controversy on that law. And I might consider asking an essay question about how that law would play out in terms of self-driving automobiles. Obviously, when you talk about military drones, it has definitely been violated by, my home country, where I came from. They're probably the #1 violator of that law. They said military drones. Now, they get around that by saying that the drones are operated by a human being, therefore it's not really a robot, it's just a remote-controlled aircraft. It's not completely automated. Robots must obey the orders given and must protect its own existence as long as that there. So these have been around, these are kind of the first rules of robotics that have been around. I can't even remember who came up with them. But I think Isaac Asimov came up with these. This is really getting more into what we talked about more in this course, and the 5 parts of a robot. You will be expected to know these 5 parts. Give an example of each of these 5 parts. A controller can be your microcontroller board, an 8051, an ARM processor, a Raspberry Pi, an Arduino, any type of controller right there. Usually microprocessor based today. Typically that would be part of your answer. Typically microprocessor or microcontroller based. And actually a microprocessor is inside every microcontroller, so therefore if you just say microprocessor based, then you cover the microcontroller as well, right there. Because the microcontroller has, as part of it, a microprocessor, memory, I/O, support chips. The manipulator, right there. The manipulator is typically the arm of a robot. The actuator is what makes the arms move, right there. So that there. The end effectors, that's the clamp, that's the magnetic, that's the pneumatic vacuum, pump or pressure. That's there. And of course, the sensors are what the robot that they're. And these slides here kind of go through again, reviewing controller connected to a computer, functions as the brain, allows the robot to be networked to other systems. That's a key thing. I'm going to have to use this pen. Is that if we look at more complex robotic systems in an industrial automation, they have to be tied to a mainframe or a computer system that controls the assembly line, controls other robots in the line for things to work in harmony. So robots don't have to be networked. My iRobot that we use at home that vacuums the floor, it maps out the floor of the room that it's vacuuming, but it doesn't talk to a mainframe computer in my house that has the floor layout of the house. Now, you could design one that does that, or you feed it the blueprints and you tell it what rooms you want to have vacuumed. And it would then, the main computer would then feed to the remote robot the pattern in which you would want to go through. That's there. So I was listening on the radio is that an interesting phenomena is that they are placing internet capability on things like floor vacuuming systems, where that it can talk to a mainframe computer someplace that they're through the internet, and companies such as iRobot, can't remember the parent name of the company that makes iRobot off the top of my head, but they had not ruled out the fact of gathering information and selling to advertisers. And one of the things that was speculated is that the iRobot could collect information from vacuuming your house on the type of dirt it picks up. So if you're the type that likes to eat potato chips, for example, and it picks up potato chip crumbs, all of a sudden, Google is now sending you advertisements for potato chip brands because the robot has sensed that you like potato chips. Out there. If it picks up cat fur, then you might be getting advertisements for cat food and cat litter. So these robots are in your home can start gathering scary information. That's there. So it is one of the things. If this is called the Internet of Things. Now like a washing machine could pick up the type of dirt it finds in your clothes, the brand of soap that you're using to wash your clothes. I mean, that is not beyond the realm of robotic information gathering. So, but that gets a little bit beyond what we're talking about in this course. But the controller does allow this networking of the robot. That's there. So we'll have a controller written by a program. You typically robots. There's a source code that controls the robot. That's developed by the programmer that works for the robot manufacturer, and then you feed it instructions on programming that there. So when I use the iRobot to vacuum my floor, I don't give it any instructions. I just hit the go and it automatically starts following the instructions. It's a little bit more complicated if you're looking at the robotic arm putting tires on a Proton automobile as it's going on an assembly line. You have to program the robot to pick up the tire and place it there, and then tighten the four lug bolts to a certain setting. That has to be programmed at the factory floor by the manufacturing engineer. And that would be probably the number one place where you would probably come across robotics. That's there. Unfortunately, we don't have there. Okay, the manipulator, it's the arm that the positions that there. The key thing here is that they come in all shapes and sizes, right there. So many resemble human hands. I showed you the first class that the one video that I have you download where they looked at humanoid type robots, the Android type. That's there. But this is what moves the end effector and sensors into position right there. So there. We do have one more lab to do, and using the robotic arm. We need to probably schedule that coming up shortly. Like I said, we missed a couple of weeks here. A simple robotic has 6 degrees of freedom, 3 up, 3 down, 3 left and right. The robotic arm that we had 3. That's a simple up, down, left, right, forward, backwards would be 3 degrees of freedom. If you look at something with a shoulder type joint, then of course it has infinite degrees of freedom. The human shoulder and the human hip have a huge number of degrees of freedom. If you look at your elbow, it only has 1 degree of freedom. This way, right here. That's just 1 degree of freedom. If you try turning your elbow this way, you get a little bit of movement, but too much, it's quite painful. Right there. And I guarantee you the knee only has 2 degrees of freedom, because I tried turning the knee rotationally and I tore my ACL that connected the top part of my knee to the bottom, and underwent several hours in the operating room to replace it. Human joints don't pan well if you extend their range of motion beyond a certain range. Same thing with robots right there. You only have so many degrees of freedom right there. And I should point out that as I look at the final exam, one of the questions might be is I might show you a robot arm and ask you how many degrees of freedom it has. That's there. In order to see if you understand this concept, that goes a little bit beyond memorization. Right there. The human elbow, 1 degree of freedom. The wrist actually has 1 degree of freedom and 2 degrees of freedom. It can rotate somewhat. Now you can't rotate your wrist beyond a certain point, but the wrist does have a degree of freedom left and right and forward and backwards. But I can't take my wrist and go up or down. I mean, it's stationary. It can move forward, backwards, this way. If I go beyond a certain range, so when you look at degrees of freedom, there may be some limitations on range. Since my stroke, my arm doesn't like to go beyond this. It gets quite painful if I try to raise my arm up beyond this point, right there. And same thing with my thumbs. That's one of the problems is my controller is bad. That's there. So here's showing an example of that. Here we've got an arm sweep that goes this way, a shoulder swivel. Now this shoulder swivel actually has only 1 degree of freedom because it'll only go this way, but it gets a second one from this rotation. We've got an elbow extension here. We've got the pitch, that's the wrist movement. The yaw is kind of the roll is this here. The yaw, I'm not sure where they're looking at the yaw. I think that's out there. But again, because we got the roll here, and which allows it to rotate. Now, this particular robot rotates more than the human wrist, right there. I'm not sure what the yaw is kind of like this type of movement. Yeah, which the human wrist doesn't do very well. That there. So, right there. Now the actuator is the mechanism used to drive the processor to a it's the motor of various types, or the valve, or the cylinder that moves the arms, or the various. Because as we look at here, when we look at the manipulators, we've got, you know, this disc that rotates. We've got the swivel the shoulder that swivels his elbow. But we need to drive this movement. In the human body, that's done by muscles, right? So when we look at the actuators, that's the robotic equivalent of a muscle. Now, I'm going back to the beginning of the semester, reviewing everything from the beginning because we've had a few weeks there. So consistent components. Again, I'm going to cover everything in 1 hour here, essentially. We've got pneumatic and hydraulic cylinders. We've got pneumatic and hydraulic rotary motors, and we've got electric motors. Now, electric motors can do linear motion using a worm gear, a type of gear. So, robotic position depends on the combination of these components. Now, in a more advanced class, if you were to look at the textbook that's listed on the syllabus, he does a lot of four by four matrices where you look at the position of each actuator and determine the position of the arms. That's kind of useless information for most people going into robotics. That's why I threw the book in the trash out there. I read the book. Yeah, I can understand it. I could teach it, and I could completely put everyone to sleep, including myself, going through that type of material. But there's a lot of research done at the upper level beyond the scope that any of you will do. But what they're talking about here is the combination of the actuators, the physical design of the arms or the manipulators will determine where things are right there. In the case of our particular robot, you would have what is the angular position of each of the 6 motors will determine whether you can pick an object up and move it right there. So a rope is driven by mechanical use that there. This is using our 2 resolvers. These there, I'm not going to go into much of this. Has got to cover, but these are 2 cylinders that there. So again, I'm not going to get into that there. The end effector is connected to the robot. I talked about that again. I'm just kind of reviewing what I did up there. It could be a gripper, a vacuum pump, scoop hook, whatever. That there. If you look at, for example, a crane is a form of a robotic arm that sends the cable down and closes and picks something up or hooks something out there. Some of the robots, and we didn't look at the robot. I did the first semester, and it's kind of a waste of time a little bit. There's one robot in the lab down on the second or first floor. It has interchangeable tools. So you can put a gripper there, you can put a vacuum pump, you can put various types. Most industrial robots are made by robot manufacturers. And I think right now the #1 robot manufacturer is Toshiba. I believe that's right. Some of the German companies were quite prevalent, but the Japanese kind of took over that there. And Mitsubishi, I know, makes some. As far as I know, there aren't any big American companies that make robots. The U.S. companies have not gone into the robot stage. The Europeans have kind of gone very greatly into the research area and coming up with new types of robot technology. But the industrial robots tend to be more in the term of the Japanese companies. I suspect there's some Chinese robots out there. They're probably copies of the Japanese ones. There's actually a book I read one time called Copycat China, so where they talk about that there. So, but again, if it has more than one arm, and this last one is kind of an interesting comment here. is they talk about the fact that a robot could have multiple arms. That there. You could have the same robot with the same controller with two arms, one to pick up the tire and another one to screw the 4 lug bolts on. Right there. And they could be totally different looking arms. And of course they would have 2 totally different types of end effectors or grippers. One would be a gripper that would pick up the tire and place it in place. That's there. And the other one would be a rotating lug bolt, or I don't know what they call it. You know, we call it a lug wrench in the States that tightens the bolts, because we call that a lug that holds the tire on. I'm not sure what the term is here. I think it's different because you follow the British terminology, and I don't know what they're. But again, you have 2 different types of arms on the same robot. No, they're in the same location on the assembly line. So do you need 2 robots? That there. You need 2 controllers. So again, they're showing, and here what they're showing is this little vacuum. That there. If you go to Intel, or well, it's Intel and Intel. I want to say Altera, but Altera was bought by Intel, so. But if you go to Texas Instruments or Intel or Freecell or any of the chip manufacturers, and they're cutting silicon wafers into little dies, those things are tiny, and they typically use a very small vacuum to pick them up, move them, place them in the plastic chip carrier, and then other robots come in and solder the leads going to the pins on the ICs. Those are completely different robots than the ones that do the lug bolts in, or place the engine in the chassis of the car at Proton. Sensors, they provide the feedback, and the 4 classes of sensors that we typically look at are position sensors. Where is the robot in space? Right there. Range sensors. How far is it from a particular object? Right there. Velocity, how fast is it moving? Or is it moving at all? And proximity, is there something there? Is it close? Proximity sensors are quite often used to determine if a part is on an assembly line, or if a vehicle is in a turn lane, to know whether or not to turn on the turn signals. So they look for something there or not there. So those are the 4 different types of sensors that there. Again, these slides should be up. If they're not up, I'll put them up again. That there. But those are the 4 types of sensors that there. So there are 3 types of power supplies or power sources for the robot. Right there. Hydraulic drive is a oil pump that pumps oil or water. Right there. Hydraulic fluid, in most cases, is a type of oil. Right there. Very similar to transmission fluid in your car. Right there. Or brake fluid. Actually, the brakes on the automobile is a type of hydraulic cylinder that when you press the brake pedal, it activates a motor that pumps hydraulic fluid to the brakes. The old manual brakes, there was no motor there, so you had to push harder. That there. Just like steering, when you steer a car today, there's a motor that helps steer it, help pump the hydraulic fluid to the steering wheel. Back in the old days, you actually turn the gears that turn that there. And I'm old enough to remember pre-power steering and power brake days. And they were quite interesting. And, kind of a side note, if your engine ever dies while you're driving, you'll notice that the braking and the steering all of a sudden becomes much more difficult because you lose that power assist right there. Electric drive, a lot of your, especially your smaller motors, will use electric drive to drive the arms. Now this is the power sources for the arms, to move the arms. And then pneumatic for very small motors, especially in areas in which oil would be bad. You know, in the IC manufacturing area, you definitely don't want petroleum oil on your ICs before you start soldering the pins. And you definitely don't want to have electric motors anywhere near, because electronic ICs tend to not like static electricity. They tend to, burn up, the transistor junctions, diode junctions tend to get zapped and fried, and the ICs don't work. Right, that there. So pneumatic drives are used in a lot of places. You'll use pneumatic drives in places where you're dealing with things such as natural gas and petroleum, where it's very flammable. You might want to avoid the use of electrical motors there. Hydraulic could be used in those situations as well. Hydraulic, these are some of the rules, and I think there was a slide later on that I said, that you should memorize it. This actually goes in the slide. The advantages of hydraulic, disadvantages that they're, the three advantages is they're fast, they can move very heavy parts, and expressive environments. In other words, that's kind of a hostile environment right there. So they occupy a large space. Hydraulic cylinders are big. That's there. And there is the danger of oil leak to the shop floor. I worked at a company where we used a lot of hydraulic motors there, and a lot of pneumatic motors, in the factory running machinery. And there was a lot of times we'd get hydraulic leaks, and sometimes they're quite hazardous. I mean, I've seen people get hydraulic oil spraying in their eyes at high temperature. That's there. As far as I know, nobody on my shift ever lost their sight because of it, but they spent some time under what they call the eye wash area. Electric drives are slower in comparison to hydraulic. Hydraulic is quicker. They're probably good for about 90% of most small robots. They use some type of electric drive. They have better positioning and accuracy. The feedback mechanisms for electric motors, especially servo motors with feedback systems, that there is much more accurate, and you can repeat that. You have the stepper motors that give you open loop control, but they're fairly accurate. They'll go so many degrees per step, and they're fairly accurate. They need to be calibrated every now and then. I talked about the satellite dish used in a stepper motor. The old printers used to use stepper motors. There's a lot of stepper motors still in use today. That there. DC drive typically uses some type of feedback control right there. So they're cleaner than the hydraulics by any means. And I said they're the most common. The one disadvantage that's not listed is that there is the possibility of electric spark, which for hazardous areas or in industries where static electricity could be a problem, you have to be able to be careful with it. Pneumatic, they're used for very, very small robots, and that they're less expensive, that their air pumps are fairly cheap. That there. They don't have as much, less degrees of freedom. You can't do much with them. I mean, they're usually only one thing. Suitable for pick and place. That there. I mentioned the IC manufacturing where you pick that there. We used to use a lot of these when I worked at Magnavox for manufacturing, printed circuit boards that they would pick up ICs and put them in place. That there. And then underneath there would be a crimper, and then we'd take it to the full solder machine, and that's how we would make electronic boards. So I've been around a lot of pneumatic robotics that they're in the electronics industry. That's probably where they're used the most. I can't think of any place in the automobile manufacturing other than electronics in an automobile where you're going to use a lot of pneumatic drives. Right there. Okay. Again, as I said, everything that I've covered in this set of slides, I've covered in other slides before. This is all review material, but it's kind of the wrap up there. Rotation, enable the rotate it straight on a horizontal plane. Again, this is kind of rotation right there. This is rotation right there. Moves its endpoint to reach a distant point. That's in and out. Vertical, up and down, right there. So we've got, these are the basic. Our robot will rotate. It will go up and down, or it can go, move its endpoint to reach distant points. It could go out or in, and then vertical, up or down, right there. So these are the two types of joints. Prismatic, which is a sliding joint. Our robot that we have in the lab does not have a prismatic joint. A prismatic joint is one that slides on a cylinder, right there. And rotational, twisting, and revolving, these are types that turn. So when we look at the prismatic, this is an example. If you look at an XY plotter, or if you look at a what do I want? I'm just drew a blank here. The thing where you etch PC boards, where it goes through and cuts holes at there. Is I've got a joint here that goes left, right, up or down, or in or out, right there. So when we look at okay, if you look at an XY plotter, you've got two arms, one that goes this way and then one that goes this way. And your pin is right here. And you can reach anywhere on that there. Typically, these are stepper motors that drive these arms left or right, right there. And that's what we're looking at here, is that here we've got one range of motion here. Here we've got another range here, and this actually has a third range up and down. Again, you would have the same thing with your pin, because your pin has to go down or up. So, and the same thing if you have like a router to cut your board into a certain shape, right there. So these are, again, the whole thing that we're trying to get across is a prismatic joint. And just put that in memory, is one that moves side to side, up or down, but it has one range of motion with a pump. Where a rotation joint is one that's similar to 90%, actually probably 99% of all the joints in the human body. I can't think of a prismatic joint in the human body. Right there. Can anybody think of it? They're all controlled by muscles, and they all pivot of some, rotate of some type. Your finger like this, your finger does this, your elbow does this, that there, your shoulder, of course, is a different type of joint right there that has multiple muscles that move in different ways. That there, your hip again. Your hip and your shoulder are very similar joints. You know, they have a pretty much infinite range of motion within the limits. Obviously, you can take your shoulder and tear it out of place. That there. So, but the human body, pretty much 90%, 99%. I can't think of any non-rotational joints right there. So those are the two types right there: the prismatic and the rotational joint. The twisting joint is also a rotational joint, and that's one that turns. Now, kind of like if you look at a car, and they're not popular as much anymore, but the old manual transmissions. If you had a manual transmission, between the transmission and the engine, there was something called the clutch. And the clutch was a round disc, and it contained asbestos material back in the days that I used to make clutches. And I used to be an expert on clutches because I spent about 3 or 4 years working for a company that made clutches and brake shoes. Before I went to college, it's what I did after the Air Force. Before college, is I made brake shoes and clutch facings. That there. So, but a clutch was a piece of friction material that, if you put it between something that was spinning, that would be the engine of the car, and the transmission, it would cause the transmission to spin with it. Right there. And when you put your foot on the clutch pedal, you would take the clutch and you would move it away from the engine, so it would stop spinning. And this enabled the car to essentially go into, where you can shift the gears without tearing up the transmission. And I actually had a car one time, this is talking about my much younger days, that had a hydraulic clutch, that the clutch hydraulic went out, and I drove it for like 3 weeks without any way of disengaging the clutch. I mean, there was a clutch, but I couldn't disengage it. So I would start the car in neutral and shove it into first while it's engaged, and then I would time my shifting from first to second in a way that I didn't tear up the transmission. And I drove that car for, like I said, 2 weeks, and I fixed the clutch and it ran fine. And it was a great little car, a little Triumph TR6. That there. Oh, it was a fun car to drive. That's there, but regardless, the clutch was not very well designed, and I finally got it fixed. But again, this is where you've got two joints that one comes in, and that's there. Almost all twisting joints are going to be connected through by some type of clutch operation, where you engage or disengage it right there. And the easiest thing I could think of is the transmission of a car. The transmission of a washing machine would also come into play. You've got a motor in the bottom that's spinning in one direction, and then you've got the agitating arms that would also twist, and you would control it through a transmission right there. So when your washing machine shifts gears, when I say shift gears, this means it's going from the wash cycle to the spin dry cycle. That's similar to a car shifting gears. So they may use a twisting joint right there. A revolving joint is one that is, again, revolving. You've got an input link and the output. That's where you're turning, moving like this there. Again, this would be something like the steering of your car. Yeah. Not really, because that usually uses a joint that goes this way that turns it. But if you want to raise, the arm of a crane, that would be a revolving joint right there, where you're picking it up like this. This is a revolving joint right there, where I'm picking up this mouse right there. So, okay. This is getting away from the whole topic of joints. That's everything that's going to be on the final exam on joints and actuators. If I was to review the first half of the semester on what's going to, I would probably write 90% of it from, those first set of slides. Okay. The advantages and disadvantages of robots: they don't have strokes and they don't call into work for a month. I missed a semester, almost a month of work last semester, and I still miss work, from time to time. So robots don't call in sick. They don't need rest, right there. They don't take naps. They do break down though. When dangerous tasks are there, a robot doesn't ask, "Are you nuts?" when it comes to climbing up a ladder to wash windows. If you asked me to climb up a ladder to wash those windows up there, I would probably laugh at you. There was a time I was stupid enough to do stuff like that, but there was a time I used to jump out of airplanes for fun too. I used to do skydiving as a sport, back when I was like 18, 19, 20 years old. And I was also in the Air Force. I mean, people do crazy things when they're in the military too, but, and the old joke is you never jump out of a pretty good plane. I said, well, you've never seen the planes that we used at our jump club. They were safer to jump out of than they were to land in. But regardless, there are things that robots can do that we find that most humans, it's too dangerous. If I want to go into a building where somebody's put a bomb and remove that bomb and place it inside some type of container, I probably wouldn't want to ask you to do that, because if you pick up the bomb and you don't handle it carefully, boom, boom, you're gone. But you can easily ask a robot to do that right there. So robots are used in a lot of areas where things are too dangerous. If I want a robot to do a weld on the International Space Station and there's no oxygen out there, it's probably a lot easier for the robot to do it than to send an astronaut out there, because he's got to suit up and he's got to out there. So robots that there can work in areas that are repetitive and unrewarding. That is probably the number one use for robots today, is repetitive work that is very unrewarding. McDonald's and a lot of fast food places in the U.S. are experimenting with robotic servers. In other words, you walk up, you put your order into a little computer or a kiosk, you swipe your debit card or credit card or touch and go card or whatever, and the robot assembles your sandwich and puts it out in front of you. When it comes time for more fries, the robot drops the fries, pulls up the fries, and you eliminate the need for people out there. And this is a lot of where society is going to, unfortunately. That's there. So we look at the fact that, and I don't know if any of you have ever worked in a fast food restaurant. I've never had. Both my sons have. That's there. And they assure me that it's some of the worst jobs they ever had, because you come home smelling like French fry grease, and if you work in a pizza parlor, you learn to hate pizza because you smell it all the time, you're around it all the time. If you work in a chicken place, you don't eat chicken much anymore. I mean, it's very unrewarding work. Now, if you're the manager and you're supervising people who are doing that work, that's not so bad. But the person frying the chicken and having to be nice to everybody who walks up to the counter and say, "May I help you? What would you like?" That's, up there. So it's not what you call the most rewarding type job. I came into work this morning. There were 6 guys on the back of a garbage truck, jumping off a garbage truck, grabbing bags of garbage, throwing it into the truck. Who wants to do that for the rest of their life as their daily job? Now raise your hand. Anybody want to do that for the rest of their life? Ride on the back of a garbage truck and go and pull out bags of garbage out, trash out of people's cans and throw it in the back of. It would be better if you had a robotic arm that went over and picked up that trash can and dumped it into the trash can. And you eliminated the fact that there. So a lot of the jobs that robots replace And this is the Donald Trump, I don't get it problem here, are jobs that we don't want to do anyway. I don't want to collect garbage, trash. I'd rather have a machine do that. I don't want to wash my dishes by hand. I'd rather throw in a machine and let it wash the dishes for me. Or one young lady in the house, do you want to wash clothes by hand? Scrub them up there? No, you'd rather throw it in the machine and let the machine do the work, right? And you'd probably rather the machine dry the clothes so you don't have to take them out and dry them. You'd probably rather have the machine fold them so you don't have to put them on the shelf, right? Up there. So robots replace work that we don't want to do. And that's really the key thing that I want to try to get across with this discussion. But they will eliminate jobs that some people do like. I know a lot of people that drive truck for a living in the U.S. Now, driving a truck in the U.S. is not like driving a truck in Malaysia. The difference is that I can get from Johor to Kampong Baru, not Kampong, Kota Baru. Let me get the names of the cities straight here. Kampong Baru is a part of KL. It's a neighborhood in KL. Kota Baru is a city near the Thai border that there. And I can get there in about 9 hours, right? Typically driving. Maybe a little longer by train. It might be a little bit longer than 9 hours. But I'm thinking about 8 to 9 hours is probably typical that there. You can't get from Fort Wayne, Indiana, where I used to live, to Minneapolis, St. Paul, where I grew up, in about 9 hours. And you haven't left the central Midwest. You're still in the same part of the country. It takes you about 8 hours to get from Los Angeles to San Francisco. And you're still in California. That's there. If you want to go from San Diego, which is near Mexico on the California border, up to near, and don't laugh when I say the name of the town, Weed, California, which is real close to the Oregon border, right there. That's about 12 hours. Right there, without traffic. That's right, right there. So truck drivers, but they enjoy their job. They're isolated, but truck driving is going to be replaced. The truck drivers are going to be replaced with trucks that drive themselves. Right there. For the most part, a lot of the truck driving was replaced by trains, but then trains can't do that final loop. But again, there's some jobs that are going to disappear. Taxi drivers, Uber is busting its tail to try to come up with ways of replacing taxi drivers. So some of this work that they're going to replace is fun work. I know taxi drivers that love their job. They love the interaction with people. They love driving around the city. They find driving fun. So not all work replaced by robots is repetitive and unrewarding, but most of it is. Coal mining. We have the coal mines in the U.S. and there's coal mines elsewhere. I don't think there's any in Malaysia. But Malaysia had the tin mines. Tin mines. But mining is dangerous, hard, back-breaking work. It's not fun work. And a lot of that's been replaced with automation. Now the disadvantages with robots. They're not creative or innovative yet. They can't come up with, a robot will not write a song that you find very appealing. Right there. So robots don't write novels. They don't write, in general, they don't come up with speeches. They would be, a robot teaching this class would be very boring. I may be very boring as it is, but a robot would be even worse. Right there. They don't think independently. Now, that's a good and bad thing with robots. When they don't think all of a sudden, we're not being paid enough, we need to go on strike. That there. Robots don't go on strike. That there. But robots don't think independently. You can't give a robot with limited instructions on how to do and tell it to go do something. Go out and change the engine of this car. You got to give that robot detailed instructions. You'll go out, you'll look at the engine, you'll figure out how to take it out, you'll pull off a manual, but you know, a human being can be innovative and think independently right there. They don't make complicated decisions. Now that is kind of changing somewhat. With artificial intelligence, robots are beginning to make more and more complicated decisions. But for the most part, you can simply say most robots can't make complicated decisions, right? They do not learn from mistakes. I was watching a documentary over the break, and it was about the teenage brain. I think most of you are a little beyond the teenage years, although some barely. But they talk about the fact that the teenage brain makes lots of mistakes. They take lots of risks. But it's all part of the growing and learning process. There's a quote by an individual that I find quite entertaining, Garrison Keillor, which none of you have ever heard of unless you've been to Minnesota and listened to Prairie Home Companion. But he simply says, with old age comes wisdom. And wisdom comes from experiences. And many of our best experiences are the result of bad decisions. You know, I'm not going to say that I've made a lot of great decisions in life. I've made a lot of stupid decisions. But I learned from them. You become wiser. That's why, you know, the old wise owl, you know, I don't know if they have talk about that there, but older people are often considered wiser. And it's not because they're so much smarter and so much more brilliant. I mean, if anything, young people are much quicker and much smarter. You know, almost every innovation today is the result of somebody in their late teens or early 20s. You look at Albert Einstein, you look at Isaac Newton, you look at all these people. They are far more productive when it came to scientific research and studies and business acumen and things like that than older people. Now, Bill Gates was a lot sharper when he was 18, 19, 20, 22 years old in developing Microsoft right there. As he got older, he became more risk adverse and he became slower to respond. When he was young, he was much more innovative. Steve Jobs and Steve Wozniak, who developed Apple computers, again, much younger and much more innovative. You know, that's not to say that they got dumber when they got older, but their ability to innovate kind of went down a little bit. Although Jobs did come up with the iPod and the iPhone as he got older, but that's it. But typically, older people have a different set of wisdom than younger people. If you're going to ask who's going to invent the next great widget, it's probably not going to be me. It's probably going to be somebody in this room or somebody your age. So young people have a different a different skill that you bring to the table than older people do. Now, when it comes to how to run a business, how to manage things, older people have experience and some wisdom there. But the younger person's where the ideas are going to come from in the innovations. But again, that they're getting back to robots. Robots don't learn from mistakes. Humans do. And robots don't adapt quickly to changes in the robot. Now, in their surrounding. Now, someone pulls out in front of you on a motorcycle, you know you have to hit the brake and steer her out of the way, right? Otherwise, bad things happen. You know, you have to program that into a robot. It doesn't know. Its job is to go from point A to point B, and something gets in its way, it just brakes whatever gets in its way. Unless you program it. So again, these are the advantages and disadvantages. And this is probably a good slide to keep in mind. Right there. How am I on time? I can go a little bit longer here. There are 6 types of robots that I'm not going to go into these great detail. These won't be on any test right there. But just kind of review them. Cartesian, again, this is the 3-point prismatic. This is like the router that I talked about, or the XY plotter. Looks like that right there. So that's called a Cartesian. And again, the reason because Cartesian is it uses the X, Y, Z coordinates, as I want to say Z, which is the American's pronunciation, to move horizontal left to right, vertical up and down, and forward and backwards motion right there. If you want to make, for example, a very, I want to say, ornamental door, plate or something that there, and you want to grind it there, you could put a grinder on the end of this and grind the metal or the wood to make a very beautiful door of a pattern. I was at there's a block of woodworks that makes the Chinese furniture. They have a number of these milling machines that they're for making wood panels for doors and table with very elaborate designs in them right there. Like, and you think that some guy sits there with a hammer and chisel and makes that table, and 100 years ago he did, or even 30 years ago he did. Now it's a machine sitting down there making it all out there with a vacuum cleaner that sucks up the wood right there. So I mean, here we're talking about an old skill of making tabletops that are very beautiful and very fancy looking, that were done by hand by somebody with a chisel, and that now it's being done in a factory. The advantage is that you can produce 100,000 tables that look the same, and they're a lot cheaper. The bad thing is I've got 100,000 tables that are exactly the same, and they lose that artmanship. That's it. Cylinder. These are for spot welding type things that they're, again, this is something rotates around a cylinder that goes in and out right there. So they rotate around this axis up and down, then in and out. So you've got two prismatic joints that go up and down. That's a prismatic joint. This is a prismatic joint that goes in and out. And this is a rotational joint that goes around. So if you look at this one here, you've got three prismatic joints right there. So again, I could put this in there and say identify the prismatic joints and the rotational joints. So this is a prismatic joint. It goes up and down. This is a prismatic joint. It goes in and out. And this is a rotational joint here. The Polar robot, again, this one has nothing but rotational joints. Well, actually, this is a prismatic joint if this one goes in and out right here. This one could be going in and out, so that would be a prismatic right there. This is a rotational here. This is a rotational here. This is a rotational here. And this is a rotational that goes up and down. So again, you have to identify where the joints are. There's one joint here that's rotational. This joint here is definitely rotational. This joint here is rotational. Now, if there is a joint here, which there looks like there is because there's a motor here. So this motor right here is driving a worm gear that extends this in and out. That would be a prismatic joint right there. And then there's also a joint here that rotates. And this looks like, again, actually, there's probably something out here, but it doesn't really show you. I'm going to treat this whole thing as the end actuator right there. So, but as you look at this here, rotational, 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 prismatic, because this goes in and out, and right there. It's a little harder to see the prismatic here. If you look at this one here, you can identify which one is. Because here this is showing rotational, this is showing rotational. Here's a prismatic. But this drawing doesn't show all the various joints on this particular robot, because this has got the rotational here. This one shows rotational here. It doesn't show a rotational here. And it doesn't show the rotational here. Those two are missing from this drawing here. Right there. But it shows the prismatic, which is, again, from this little, right there. And this is just a little motor that turns right or left and that pulls it in or out, right there. This is the selective compliant assembly robot, right there. two parallel right there. This is a rotational here and a rotational here, and then a prismatic that goes up and down right here. So two rotationals and a prismatic right there. And the articulated that there, this is the full blown. This actually has nothing but rotationals. Rotational here, rotational here, rotational here. This doesn't extend in or out, and then a rotational here. So look at the drawing and see that they're all rotation. That there, and I'm not going to get into any of these particular. This kind of summarizes all that, but not very well. These are some examples. We've talked about these many times. Welding, spray paint assembly, out there. Pictures. You know, again, I'm kind of wrapping up this discussion right there. I have one more review session, and that's talking about sensors. I talked about sensors before. I'm not going to get into sensors today. I've talked, my normal hour. I can't talk much more than an hour. I'm usually at there, but I will probably talk about that and then talk about the next lab on Thursday. We meet on Thursday, right? Or Wednesday? Thursday. That there. And then the lab, I'm going to have you do on your own next Monday. Yeah, that's there. And I'll probably just be up in the office while you're working on the lab. Then I'll talk about PLCs to finish up the course. So I've got one more lecture to kind of review sensors, but this lecture probably covers 75% of what's going to be on the final exam on the robotics side. That's there. So, and I will have a test over this. Once I cover sensors, I'll put a test up there that covers this material, and that's about 2/3 of what's on the final exam is what's going to be on that test right there.